Hello friends, welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry. We were discussing unit 7 equilibrium, and in this video we will discuss about important features of equilibrium constant and applications of equilibrium constants. First come to important features of equilibrium constant. Expression for equilibrium constant is applicable only when concentrations of the reactants and products have attained constant value at equilibrium state. The value of equilibrium constant is independent of initial concentrations of the reactants and products. Equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by a balanced equation at a given temperature. That is, if we change the temperature, equilibrium constant will change. But if we change the initial concentration, equilibrium constant will not change for a particular reaction. The equilibrium constant for the reverse reaction is equal to the inverse of the equilibrium constant for a forward reaction. If for forward reaction equilibrium constant is Kc, then for the reverse reaction this K dash C is equal to 1 by Kc. If equation is multiplied by the factor n, the equilibrium constant Kc double dash is related to the equilibrium constant of original reaction, that is Kc, by this relation. This Kc, this is the equilibrium constant for original reaction, and if this equation is multiplied by the factor n, then the equilibrium constant for this reaction is represented as Kc double dash, and this is related to Kc according to this formula. Okay, Kc double dash is equal to Kc power n. This n is the factor by which that equation is multiplied. Okay. Applications of equilibrium constants. Equilibrium constant is used to predict the extent of a reaction on the basis of its magnitude. Second one is predict the direction of the reaction and to calculate equilibrium concentrations. Now we will discuss one by one. First come to predicting the extent of a reaction. The magnitude of Kc or Kp is directly proportional to the concentrations of products as these appear in the numerator of equilibrium constant expression, and inversely proportional to the concentrations of the reactants as these appear in the denominator. We already discussed when we write the expression for equilibrium constant, concentration of products are written in the numerator and concentration of reactants are written in the denominator. Okay. This means that high value of K is suggestive of a high concentration of products and vice versa. Okay. Now, if Kc is greater than 10 to the power 3, products predominate over reactants. That is, if Kc is very large, the reaction proceeds nearly to completion. For example, H2 gas plus Cl2 gas will convert into 2HCl gas at 300 Kelvin. It has Kc is equal to 4.0 into 10 to the power 31. If Kc is smaller than 10 to the power minus 3, it means reactants predominate over products. That is, if Kc is very small, the reaction proceeds rarely, or we can say it is reactants are more and products are not formed. For example, N2 plus O2 converting into 2NO at 298 Kelvin, Kc is very less, 4.8 into 10 to the power minus 31. If Kc is in the range of 10 to the power minus 3 to 10 to the power 3, appreciable concentrations of both reactants and products are present. For reaction of H2 with I2 to give Hi, Kc is 57.0 at 700 Kelvin. It means at the equilibrium condition, both reactants, that is H2 and I2, and product Hi are present in the appreciable concentration. Okay, this can also be represented by this figure. This is the increasing order of Kc. If this is extremely large, it means a reaction proceeds almost to completion. If this is negligible, or we can say less than 10 to the power minus 3, reaction hardly proceeds. And if this is Kc is in between these two ranges, both reactants and products are present at equilibrium. Okay. Now, second one is predicting the direction of the reaction. Okay. Now, at this time, we will introduce one another factor, that is a reaction quotient, that is Q. If we write QC, it means we are considering the molar concentrations of reactants and products. And if we write QP, then we are considering the partial pressures of reactants and products as Kc and Kp. Okay. Now, how can we define this reaction quotient? Actually, this is defined in the same way as the equilibrium constant Kc, except that the concentrations in QC are not necessarily equilibrium values. Clear? Simply we can say this QC is also the ratio of concentration of products to concentration of reactants, and each concentration term raised to the power equal to stoichiometry coefficient, but these concentrations are not equilibrium concentrations. Okay. So if this is hypothetical equation, in the same way like we have written Kc, we can also write QC. Okay. But again, remember, these concentrations are not the equilibrium concentrations. Okay. Now, if QC is greater than Kc, it means the reaction will proceed in the direction of a reactants, that is reverse reaction. If QC is greater than Kc, simply we can say if QC is greater, it means concentration of products are more. Okay, that's why to reach at equilibrium condition, these products will convert into the reactants. Reverse direction will taking place. If QC is smaller than Kc, the reaction will proceed in the direction of the products, that is forward reaction. And if QC is equal to Kc, the reaction mixture is already at equilibrium. Okay. The reaction quotient QC is useful in predicting the direction of reaction by comparing the values of QC and Kc. With the help of this diagram, you can understand if QC is smaller, this will proceed in the forward direction. Okay. And if QC and Kc both are equal, then we can say reactants and products are at equilibrium condition. If QC is greater than Kc, then products will convert into the reactants, that is reverse reaction will take place. Okay. We can also write QC is smaller than Kc, net reaction goes from left to right. Okay, left to right. See this condition, QC is smaller than this condition, that is reactants will convert into product. If QC is greater than Kc, net reaction goes from right to left, that is products will convert into reactants. And if both are same, no net reaction occurs, reaction is already at equilibrium. See one question. Problem 7.7. The value of Kc for the reaction 2A converting into B plus C is 2 into 10 to the power minus 3. At a given time, the composition of reaction mixture is A, concentration of A is equal to concentration of B, that is equal to concentration of C, and this is equal to 3 into 10 to the power minus 4 m. In which direction the reaction will proceed? Okay, in this case, Kc is given. We have to find out QC. This is QC. Okay. According to this reaction, we can write the expression for QC, concentration of B, concentration of C in numerator, divided by concentration of A power 2. Put the values. All these concentrations are equal. So, this QC, put the value, and if we solve it, we will get 1. Now, just compare. This is 1 and KC is this one. So we can say QC is greater than Kc. So reaction will proceed in reverse direction. Now one more application of equilibrium constant, we can determine the or we can calculate the equilibrium concentrations. That is calculating equilibrium concentrations. Now, different steps are there. First step, write the balanced equation for the reaction. Then step 2, under the balanced equation, make a table that lists for each substance involved in the reaction, and these things we have to list. Initial concentration, the change in concentration on going to equilibrium, and the equilibrium concentration. Take X as the concentration in mole per liter of one of the substances that reacts on going to equilibrium. Then use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. Then in step 3, substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve for X. And step 4, calculate the equilibrium concentrations from the calculated value of X. Let us discuss one example to understand this. Problem 7.9. 3.00 mole of PCl5 kept in 1 liter closed reaction vessel was allowed to attain equilibrium at this temperature. Calculate composition of the mixture at equilibrium. Okay, and Kc is given. First step, write the balanced chemical equation. PCl5 converting into PCl3 plus Cl2. Okay, then we made this one table. In this table, first we written initial concentration. Initial concentration of PCl5 is given 3.0. And when reaction is not started, initial concentration of PCl3 is 0, Cl2 is also 0. And let X mole per liter of PCl5 be dissociated. Okay, then at equilibrium, the concentration of PCl5 becomes 3 minus X because X moles dissociated. So remaining concentration of PCl5 is 3 minus X. And according to the stoichiometry of this equation, if 1 mole of PCl5 is decomposed, then we will get 1 mole of PCl3 and 1 mole of Cl2. And we said that X mole of PCl5 dissociated. So X mole of PCl3 and X mole of Cl2 will form at equilibrium. Clear? Then in step 3, write the equilibrium equation. Kc is equal to concentration of PCl3 multiplied by concentration of Cl2 divided by concentration of PCl5, and this is given. Kc is given 1.8. Okay, now put the value of PCl3, Cl2 and PCl5. PCl3 is X. PCl2 is also X. So this is X square. And in the denominator, concentration of PCl5 at equilibrium is 3 minus X. Okay. And if we solve this relationship, okay, we will get this X square plus 1.8X minus 5.4 is equal to 0. And if you solve it, then we will get X is equal to 1.59. Okay, X is equal to 1.59. This is the quadratic equation. I think you are able to solve it. Okay, then what is X? X we assume that is X mole per liter of PCl5 dissociated. So we can say concentration of PCl5 at equilibrium is 3 minus X is equal to 3 minus 1.59 is equal to 1.41 m. And at equilibrium, concentration of PCl3 is equal to concentration of Cl2, and that is equal to 1.59 m. Okay, thank you. Subscribe my channel to get the next video from this chapter.